Okay, I think that we can start. Before jumping the lecture, let me give you some administrative stuff. As you can see from Portata Didattica, I have uploaded the voucher list. I uploaded the first document yesterday, and then this morning I was able to finalize the assignment because last night NXP provided me with the last missing vouchers. So if you look into Materiale, Documents, you will find voucher assignment V1, where you have your ID and a code. That is the voucher that you can use to get the needed board with a 50% discount and free delivery. As I have received a smaller amount of vouchers compared to the number of students enrolled in this class, I decided to assign vouchers only to the students that are enrolled in this class for the first time. It could be the case that you just graduated in the past weeks, and so you haven't yet finalized the enrollment in the master degree. So you are not formally enrolled in this class yet, and so your name does not, your ID does not appear in the voucher assignment. If this is the case, just send me an email, I will provide you a voucher, okay? I have some buffers, so I still have some vouchers available, and upon needs, I will provide it. These vouchers are intended for one use only, so please use the one assigned to your student ID. In order to get the board, the procedure is the following. You have a link here on Portata Didattica. You have to paste it on your browser, so you are directed to the NXP page with the Freedom K64. Then you have to take buy, and then if you want to get the board using the voucher, you have to select buy direct. This is because you are not procuring the board through a distributor, but you are buying this directly through NXP in the US. So if you click here, you have to log in first. You have to create your own login. Then you sign in. There shall be a page like this one where you put the quantity that will be 1. And then here you have the coupon number. This is the place where you have to put your voucher. Then you do update basket and proceed to checkout. With this approach, you will see that the price is updated and the shipping will be for free, okay? So this is the procedure that you have to follow if you want to get the board through the buy direct using the voucher that I gave you. Then the second announcement, the second administrative stuff, I will be on a business trip on the April 27th and 29th. So last week of April, we have no lecture, okay? So please update your scheduling so you are free in the slots for my class in that time. Then based on what happens in the next month, we will see whether it is we need to recover some of these lectures. If this is the case, depending on how the progress we do in the next months, I will schedule an extra lecture and will let you know. But this is not granted yet. It depends on the needs, okay? But anyway, you will be informed through Portata Didattica. For the moment, please take note that April 27th and April 29th, we have no lectures. Okay. Now, I think that we are done with the administrative stuff. We can start looking into the lecture of today. Today, I'm starting introducing you to the usage of Simulink for code generation. So we will see few things through the slides, and then we will have a practical session. I see that most of you has the laptop, so we can do something together, doing some exercises. So the content that I'm about to present is slightly modified with respect to what is on Portata Didattica already. Sorry if I wasn't able to update this earlier, but I just finished yesterday to do the modifications because I recognize that the material shall be presented in a slightly different manner. So please take few notes in this half an hour of looking into this content, and then you will find the updated slides by today. So let me start by pointing out which is our goal, so that we do not overlook something. The goal is to generate real-time software starting from Simulink models. So from what we have seen in the last lecture, we are enforcing a model-driven engineering approach. This means that we will model the plant that we want to control, we will model the controller, then we will generate the code out of the controller model, either using algorithm export or full executable export. This is depending on the target platform that we are about to use. But at the end, whatever is the target, we want to generate real-time software. So what does it mean that we are generating real-time software? This means that we are working under the following assumptions. We are working with hard real-time tasks. So our code is encapsulated into a task. This task is subject to hard real-time constraints. This means that the deadline cannot be missed. Our task cannot take endless time in doing the computation. The task must produce the output within a fixed and known amount of time, and this is the deadline. Then the task is periodic. This means that our application will be seen on a temporal basis as an infinite sequence of identical instances that are periodically released. What does it mean? If we look at our software, our task will be task tau. That is the task, so the element in the operating system that we are using that will encapsulate the code resulting from code generation of the controller. So tau is the task that implements the instructions that put together, they give the same behavior as the model, the controller model, okay? Then this task is released periodically. Every t time, we have a new instance of the task that is released. So this means that, let's imagine this is time 0. We start running the instance 0 of task tau. This shall complete by deadline t. So this is the last time for which the output of tau must be produced. If it is produced earlier, that's okay. If it is produced later, the execution is aborted. So the task does not produce any output. Then at time t, we release a new instance of task tau. So we have tau 1. Again, the task evaluates the inputs, generates the outputs, and then at this time here, it is completed, and so a new instance of the task is released, that is tau 2, and so on and so forth. So since the beginning of the operation of your system, it will behave like this. So you will have an infinite sequence of identical tasks that are periodically released, okay? Then the period, for the sake of simplicity, is set equal to the deadline. So we have just one temporal parameter that is t, the task period. This is a periodic task, okay? It is not an asynchronous task, it is not a sporadic task, it is a periodic task, okay? Then, this is what we want to achieve. We want to achieve something that behaves like this. It's a piece of software that is composed of a task that has a specific behavior depending on what the model says. This model shall be scheduled by an operating system or a scheduler to provide such a kind of behavior. So it is very likely that we will have at least a timer that is able to expire every t milliseconds, seconds, whatever it is, the time unit that is used here. And upon expiration, tau is executed. It could be as simple as this one, like, for example, using a timeline scheduling that you may remember from operating system for embedded system or from real-time operating system class. It could be something more sophisticated. This could be a task that has been created within an operating system like the Micrium MicroCOS that we have seen together, if you are from a computer engineering class. It could be a process within a Linux operating system. No matter what, this is the way in which the application behaves. An infinite sequence of identical tasks that are instantiated, that are released periodically, okay? Then, this is where we want to go. Then now let me show you where we start from. We start from here. We start from a model in Simulink. A model in Simulink is defined through three elements. One is the set of inputs that we have to process. The other one is the set of outputs that are produced by the model that processes the input. And the third element is the state of the model. This is because our model, no matter how complex it is, no matter how many blocks you have, can be described through two equations. One equation, the equation lambda, is the equation that takes the inputs at the current time, takes the state of the model at the current time, and computes the output. What is the state? The state is, I would say, a logical element that tells what happened to the system since time 0 to time t. Let's imagine our system as a kind of memory that is able to keep track of the events that modified the operation of the model from time 0 to time t. So this memory is conveyed within the variable m. This could be, for example, a counter. Let's imagine that we have an element in our model that counts from 0 onward at each execution step. So this is something that requires a memory. We have to remember to what point of the counting we are to tell which is the next counting point. So the state is part of the definition of our model. As I said, the function lambda takes as input u, that represents the input applied to the model at a given time, takes the state of the model at that given time, and tells you which is the output of the model at that given time. So this is the function to update the output. Then, besides this, we have the state function, that is the function that we call delta, that is responsible for taking the current input, taking the current state, and deciding which is the next state. let's say we have a counter, we have to increment the counter by a quantity 1 that is produced to ut, and the counter value is 5. Delta is just a plus, so the next value of the state, the next value of the counter will be 6. 1 given into the input plus 5 current state. So next state will be 6. Okay? Is this clear? Okay. So these are the elements that defines the model. These are the elements that are designed using the Simulink schematic editor. The interconnection of blocks and the types of blocks that you put together on this schematic defines implicitly lambda and delta. So T is the time, U is the input, Y is the output, M is the state, delta, that you can see here, is the step size. What does it mean? Given the current time T, we define the next time for which we want to evaluate our model as T plus delta. So delta is the smallest amount of time that we take into consideration. It's a kind of time quantum. So for me, for the model, now is corresponding to time t, then, so the next instant of time corresponds to time t plus delta, okay? Then, Simulink makes use of an algorithm that is known as Simulink solver to evaluate the output and the next state of your model, starting from the current input, starting from the start simulation time till either infinite or the end simulation time. You may have seen this already. When you look into the Simulink schematic, you have the capability of specifying for how long you want to do the simulation, the stop time. It could be, typically it is 10 seconds, but you can write infinite if you want to have the simulation that lasts forever, or it could be whichever other number that is relevant for your application. Let's say you are simulating a dynamic behavior of a braking that takes place over a time of 9.2 seconds. It could happen. This is what we are doing these days for a project that we have. So the stop time will be 9.2. The algorithm that Simulink uses to evaluate the model throughout all the simulation time that it has to take into consideration is called Simulink solver. So the Simulink solver behaves as follows. So given a certain starting time t, for which the model is subject to input ut and to state mt, the solver computes the output. So yt is equal to lambda ut mt. So basically, we just update the output. Then the solver computes the next state. So starting from the current input, the current state, the state function will tell which is the next state that the system, that the model has to reach. And this is the value of the state at the next time. The next time is t plus delta. Then the solver computes delta, computes the next time. Depending on the options that we selected, this could be very simple or pretty complex. It depends on the algorithm, on the solver algorithm that you decided to adopt. For the moment, let me just say that the solver contains a special function to tell, based on the shape of the model, based on the current time, which will be the next time. So once all these operations are completed, the solver updates time, so t becomes t plus delta. The status of the system at the current time becomes the value previously computed, and then we repeat from 1. What is described here in step 1 is called simulation step. One simulation step for the Simulink solver consists in evaluating the input, the current state, to tell which is the next state and the output of the model. Then the next time is computed and the cycle is repeated. So let's imagine that delta is the quantum in which you divide the time axis. So this means that you will solve your model every delta, starting from 0 to the stop simulation time. Okay? Is this clear so far? Then delta, as I was saying, depends on the adopted solver. If you look into the configuration of Simulink, you have multiple options here. You can have fixed step solvers, or you can have variable step solvers. The fixed step solvers are those that are based on a value of delta that is chosen a priori. So once you configure your Simulink solver, you select fixed step solver, you provide the value you want to use for delta, or you select auto. So what is happening here is that Simulink analyzes the model before starting the simulation, tells which is the value of delta to be used through all the simulation in case you adopted auto as a configuration parameter. Otherwise, it sets delta to the value that you specified, and then that value is used in any time instant of the simulation. So whether you use 100 steps or 10 steps, each step will be based on the very same delta. Let's say delta is set to 10 milliseconds, then your model will be solved with a time quantum of 10 milliseconds. Okay? Every 10 milliseconds, the inputs are sampled, the outputs are produced, and the next state is evaluated. It is clear that the smaller the delta is, the better is the accuracy with which you solve the model, especially if the model is made of a set of blocks and it is responsible for processing a set of inputs that changes very frequently. At the same time, the shorter the delta, the higher will be the computing time, because for every delta, your model will be solved. This means that you run the algorithm that takes the input, takes the state, generates the output, update the state. Okay? In case of variable step solvers, delta is chosen at each iteration of the solver. This means that for the time 0, we could have a very narrow delta that will be 1 microsecond. Then for the second iteration, we can have 2 microseconds. For the third iteration, we can have half a microsecond. For the fourth iteration, we can have 5 seconds. It depends on what the solver algorithm decides based on the type of blocks that we have on the model and on the frequency of variance inside the inputs. So you have to choose between the two. I imagine that so far you always use the variable step solver like OD4, OD3, or something similar. So basically you never take care of selecting the solver. You just open Simulink and you use the default values. Is this the case? This is typically what happens when you use Simulink for modeling mechatronic systems. You care about the model of the plant, so you are looking for the maximum accuracy, and so you just try to look into the best that Simulink can offer in terms of computation speed and quality of the results. And this is what is normally provided by variable step solver and continuous time solver. The other elements that you can tune when defining the solver that you want to use is the way in which Simulink has to deal with time. You can have a continuous time solver. This means that delta, whatever it is divided in multiple sub-instances of time. Your model is solved for each of these small sub-steps, and then the result of the simulation for the current step is obtained by integrating the values produced by the model at each sub-step. So in this way, you consider the time as continuous time. You have potentially an infinite amount of time instance within delta. This is normally the default configuration of Simulink because it is the one that provides the best approximation of your simulation. Another option is the discrete time solver. This means that the time is a discrete time. There is no infinite sequence of time instance in between two time steps. Now is time step t, then is time step t plus delta. And here you solve the model for t, and then you solve the model again for t plus delta. There is no evaluation of the status of the model in between. So you have a number of possible options here. For what we want to achieve, that is building a model whose software behaves like this, we have to select the solver configuration as follows. We must have a discrete solver with a fixed step, and the step size delta shall be set equal to the period of the task t. If you think in terms of Simulink to this picture, we can read this in this way. This is the starting time of the simulation. So here is where we evaluate the input and the current state of the model. Then we solve the model, and so we generate the output corresponding to the current state and to the current input. We update we compute the next state. Then we update t to the next time step, t plus delta. So we move to this point here in time where we re-evaluate our model. So in this way, you can see that the behavior of the Simulink solver is exactly what we want to achieve. It's the same behavior of a software routine. So what we have here is the need for selecting the solver configuration as discrete solver, and then we have to select the step size so that it is equal to the period of the task. In this way, our model, once translated into software and executed on a platform that is able to call the software corresponding to the model every t period of time, will produce a software that behaves exactly as the model that we specified. Okay? Is this clear? Okay. So it is time to move to an example. So let's try to build a simple example in Simulink that does the following. So you have to draw a Simulink model containing two subsystems. One is the plant, the other one is the controller. Why I am pushing you to do this since the beginning? This is because in our model, we always have two components, the plant and the controllers. The plant is not intended for becoming a piece of software. This is something that will not be deployed on the target. The plant is just a representation, abstract representation of the physical phenomena that we want to control. So it is something that we want to have because this is what we will use to tune the controller, to design the controller. And then we have another subsystem that is the set of Simulink blocks that shall become software. That is the real piece of software that we are about to run on our target. So we need to have the model of the controller separated from the model of the plant in such a way that we will generate code only for the controller. Then what we have here were very simple. Inside the subsystem for the plant, we have one input that is terminated, that is the input coming back from the controller. Then we have a pulse generator to give something as input to the controller. And then the two are plotted through a scope. For the controller, we have a very simple buffer. We take the input, we multiply by 10 through the gain element, and then we produce the output. Here we will use a solver with fixed step discrete time with 10 milliseconds of step size, and then we will use the code generator to see what is happening when we translate the controller into code. We will see all the steps together so we can understand what we have to do here. So let me switch to Simulink, or let's say to MATLAB. I hope all of you has the very same version of Simulink, so we'll have no surprises here. So what we have to do is to create a folder. Then we can create a subfolder in it. And then we can create a new Simulink schematics. This can be done through new Simulink model. In the new version of Simulink, you will have a kind of wizard that allows you to select the template you want to use for the modeling. If you click on new Simulink model, you have something like this, where you already have some templates of projects already prepared for you. You can select on fixed step, and then you will see that a blank page of Simulink is created that you can start populating with the elements you want to use out of the Simulink library browser. Let me open this model that I already prepared. Okay, so what we have here is a very simple model with the plant and the controller. If you want to build this top-down, you have to open the library browser, and then you select among the commonly used blocks the subsystem. You drag two instances of the subsystem on the Simulink schematics, and then you connect them. Then you can double tap on the subsystem, and you can start putting elements into this subsystem. Once you instantiate one subsystem, Simulink produces you an empty subsystem with just one input and one output and the pass-through. That is, the input is directly wired to the output. Well, you can modify this by adding the terminator and the pulse generator, and then the scope. This is for what concerns the plant. The pulse generator has been configured to have an amplitude of 1, a period of 1 second, and a pulse width of 50%. This means that you have a square waveform with a 50% duty cycle. The pulse stays to 1, that is the amplitude, for half a second, then stays to 0 for half a second, and then it repeats. Okay. well, this is very trivial, so I'm not going to spend too much time here. And then also for the controller, we have very simple schematics. We take the input, we multiply by a gain set to 10, and then we produce the output. Okay? So this is nothing very complex. Let me bring your attention to one element that is more important, that is the configuration of our model. If you tap on the model configuration parameter, you will see that the configuration pane is opened, and here we can make some observations. First of all, the first element that you have on this configuration pane is the solver. So the tab that you have on top of the list on the left of your configuration parameters is the solver. This is the portion of the configuration that allows you to select which is the solver algorithm to be used in the simulation. This is very important because it defines the way in which Simulink Solver will perform the analysis of the model, and then it also has an impact on the way in which the code will be generated. Here, as we selected a fixed step design template, we shall have as solver option fixed step, and then discrete, no continuous state, no continuous time. Then it is very likely that if you open the additional options, you will see auto as a fixed step size. This is the default for the configuration. Here we have to specify 0.01, so the 10 milliseconds that we decided to use as our step size. Where this value comes from? This value comes from the specification that somebody gave us about which is the period for which our code can be invoked on the target. So this is something that either is given to us, the architect says, well, you can call your model every 10 milliseconds, or this is something that is produced by you when you analyze your system. You analyze the plant that you have to control. You decide that in order to have a robust control, you have to apply the control algorithm every 1 millisecond. Then the software that will run the control algorithm must be executed every 1 millisecond. This means that the solver must use a step size of 1 millisecond when simulating the model specifying the controller behavior. Okay? So here is where we type, for the moment, 10 milliseconds. This is our assumption. Once we completed this configuration, we click on Apply, so that from now on, every simulation will take place using these parameters. Then we can look into the other elements that we have here. These are relevant for giving some constraints to the translator, to the tool that will take the Simulink model of the controller and will translate this into software. So you may remember the picture that we have seen the last lecture, where we have a flow, where we have the model, then we have the transformations that are applied to the model to generate the artifact. The transformations are controlled by a set of transformation rules, and the artifact is depending on some parameters of the platform that is going to be used to run the code corresponding to the model. So here, by tapping on hardware implementation, we can specify some of the parameters of the hardware that is going to be used to run the software corresponding to the model. In particular, you can select the board you want to use, and here you have a list of options depending on which are the packages that you have installed in your Simulink, in your MATLAB system. For the moment, I think you haven't installed any platform support package, so it is very likely that you have here either none or get a hardware support package. You shall not have Cortex M3 QEMU or Freescale Freedom K64F. Not yet. When you will install the platform support package, you will have that. Then you have the possibility of specifying some properties of the computing platform that you are about to use. In particular, you can select the device vendor manufacturer, the device manufacturer. That is, you can select whether you want to use an ARM-compatible processor, or if you want to use an FPGA, if you want to use an Intel, or whatever else. So for us, it is fine to select ARM-compatible. Then, if you want, you can also select a specific family for each manufacturer. So among the ARM-compatible, we select ARM Cortex. What is the purpose of this? The purpose of this is to define which are the data types that are available on the device that is going to run our code. Why this is needed? If you look into the Simulink schematics, you will see that you can use signals belonging to a predefined set of data types. We have double, we have integer, we have Boolean, and so on and so forth. Those are the native data types of MATLAB, of Simulink. But these are real only when we are working in the Simulink domain. When we are working on the target platform, we don't have doubles, we don't have integers, defined as Simulink defines them. We have to make a mapping. We have to tell, well, the integer corresponds to this data type. The double corresponds to that data type, and so on and so forth. This is because on a specific target, you can have the double specified over 64 bits. On another one, it could be 32 bits. On another one, it could be 18 bits. It depends on the target. So, when instructing the code generator what to do, you have to specify some of the properties of the target platform so that the code generator is able to produce code that can fit on that computing platform. Okay? That's why we have to select these parameters. Then again, when you are done, you tap on apply and you can move forward. Here, we can look to the code generation subsection that, as you can see here, is made of a number of options. So let's select first code generation. Code generation is the name of the set of parameters that provides further inputs to the embedded coder, that is the translation tool, so that you can instruct it how you want to have your code generated. The first thing that you have to select is system target file. The system target file is the list of transformations that you have to apply to your model to generate code. So basically, this is the file that contains the transformation rules. the one that we have seen on the concept block diagram last time. As you can see here, we have a number of different options. Well, it is not relevant entering the details of each of them. What is relevant is just to say that for each of these, you have different transformations that are applied. The one that is relevant for us is ERT.TLC that corresponds to embedded coder. This is the set of rules that we want to use. We will not go in the details of this. We will not look into ERT.TLC. Let me just say that this is something that you can modify. So you can fully customize the way in which the model is translated into code. For now, let's say that we select ERT.TLC. Then, depending on the template that you select, you can see that the list of options that you can select will change. This is because, depending on the template, you may have more or less transformations. Each of these can be customized. So, once we select ERT.TLC, we tap also on Generate Code Only. This is because we don't want to have the code generated by this tool to be compiled into something that will be then be available for the target board that we are using. For the moment, we don't want to do build process. We just want to generate the code. Then it can be useful to tap on report. Report tells embedded coder what to do once generation is completed. So basically here you can have a report to be opened automatically for you so that you can navigate the model and you can identify the code corresponding to the model and vice versa. So we select create code generation report, open report automatically, and then we tap on each of these so that we are able to navigate the model and the code. Again, once we are done, we apply. Then it could be interesting to tap on interface. Here is one of the configuration parameters that tells how the code should look like once generated. So let me say that embedded coder is able to generate different styles of C code with different prototypes, with different encapsulation of input, outputs, and states. Let's say that there are a number of possible options here. The one that is relevant for us is that we select reusable function. So our function resulting from the code generation shall be taken and embedded in another program in a simple form. So our function will be self-contained. They contain all the arguments that are needed to evaluate the model without the need for additional global variables. So once you are in the interface section, you have to select code interface packaging as reusable function. Okay? Then finally, we can customize the code placement. The code placement is the set of configuration options that tells embedded coder where to put the files generated from the model on the file system. You can have multiple files, you can have compact description. Well, what is relevant for us is that file packaging format must be compact. This means that embedded coder generates the minimum amount of file needed for representing as C code your model. Okay? So you select file packaging format as compact. Okay? Then, when we are done with this, well, we can do, for example, simulation of the model just to check whether it is doing what we are expecting. And indeed, we see that we have a behavior where we have an input that is a square waveform with 1 second period, 50% duty cycle, and then the output is multiplied by 10. So indeed, the model is doing what we are expecting. Anyway, so this is 10. Well, there is probably a problem with the display. This is 10, this is 0, this is 1. So you can see the yellow one is the input, and then the blue one is the output. So nothing special, it is behaving as expected. So now we can generate the code and we can see what is happening. While we are working at this level, we have a subsystem for the plant, a subsystem and a subsystem for the controller. So we have more than what we want to translate into software. So we have to select the controller by tapping one time on the controller subsystem, and then in the build model option of the toolbar, we select build selected subsystem. This means that embedded coder will be invoked and it will be asked to translate into code only the controller. So this will take some time. We have this option that is open. For the moment, let's just tap on build. We will come back on the meaning of this later. Then this will take some time because the building process can be long. We can have a look here at the diagnostic to understand what is happening. You can see that code generation do some operation, and then at the end, when the build process completed successfully, we have the code generation report. This is the summary of the operations that have been done on the model. We can look into the subsystem report. Where is it? Okay, we can look into the static code metrics, for example, to have a quick summary of what is inside our model. As you can see here, embedded coder tells us that it generated one C file, two H file. We have 139 lines of code out of 334 lines of file content. This means that we have comments that makes the number of lines in these files grow. Then we have three files that are generated: rtw types.h, controller.c, controller.h. And here on the bottom you have some information about the dimensions of the data structures that are used in this source file. And then you have here the generated code. You have the modded file, controller.c, controller.h, the utility file rtw types.h, and then ertmain.c. Let me switch back to the presentation so that I can give you a better description of what is the purpose of all these files. So remember that our model is controller. This is what we want to translate into C code. Okay? So using code generation algorithm export, this is because we do not have any platform-specific blocks in our model, and so we are not generating the full executable that can be deployed on the board, but we are just exporting the algorithm implemented by the controller, we have this result. So this is the Simulink input, so the controller model with input, state, and output variables. And then this is the set of files that has been generated. We have ertmain.c. ERT is the name of the template that we used. If you remember, we selected ert.tlc when configuring the code generator. So ert_main.c is the main file generated for the embedded real-time target. Then we have controller.c, controller.h. These are the two, let me do this. Let me call this block model, otherwise you can miss something. So let's say that the subsystem is called model. Model is the name of the subsystem in Simulink that we translated into code. So model produces model.c and model.h. Model.c is the source code for the model. So here you have the instructions that implements the functionality corresponding to the Simulink model. Model.h is the header file with the definition of the data structures that models.c uses. rtwtypes.h is the include file with the hardware-specific data types. So what's the meaning of all of this? Well, let me explain in detail this. So model.c contains the instruction that defines what the model is doing. So basically, what we are expecting to have here is something that, when executed as a C program, behaves as the simulation does. What Embedded Coder is doing? Embedded Coder produces 3 functions for each subsystem. These functions are initialize, step, and terminate. Initialize gets as input the model state, the model input, and the model gets as argument the model state, the model input, and the model output, and performs some initialization operations like resetting the model state to prepare the execution of the model. Then we have terminate. This is a function to clean up the memory after the last execution of the model. And then we have the step function. The step function is the most important function of all. The step function takes as input the model state, the model input, and the model output, and it executes one simulation step. So when you have the Simulink model and you ask a simulator to advance time by one simulation step, so for evaluating at time t input, output, and state, and then to adapt the time from t to t plus delta, well, you are executing one instance of step. Okay? So step is the function that contains the code corresponding to the behavior of the model during one simulation step. Then rtwtypes is the include file that maps the data type that are native in Simulink on the hardware-specific data types. Here you can see an example. Char is one of the data types that are native in Simulink. Our code will make use of char. This is because the code is generated starting from Simulink. So in Simulink, you design your schematics, you select the properties of the different objects, for example, of the different inputs, and one of these is char data type. Then, once our code is generated and it is deployed on the target, char, that is the Simulink data type, must be represented in terms of the data types that are known on the target. And for example, we define the char data type as an integer over 8 bits. Int 8 underscore capital T means integer over 8 bits. So in our platform, we have the hardware-specific data type that is integer over 8 bits. In Simulink, we have the native data type that is char. rtwtypes.h makes the association. So from now on, when we compile our code, we have that the char data type that is found in the model, that is found in the code corresponding to the model, will be translated into the hardware-specific integer over 8 bits. Okay? So this value comes from the customization that we did in Simulink using the configuration parameters when selecting the hardware implementation. If you open the configuration parameters, you select the hardware implementation tab, you will see that there is a portion on the screen that tells you how many bits you want to use to represent the char. And guess what? It is 8. This is because here we have the correspondence between char with int 8. Okay? Is this clear? Then we can have a look at the main.c. Main.c, ERT-main.c is a kind of glue that brings together all the files that have been generated. I am using a different color here just to say that this is not model specific. This ERT_main.c is always the same, no matter how complex your model is. This is because the ERT_main.c is template specific, not model specific. If you select ERT.tlc, whatever is the model, you will always have this file. And the general idea of the file is the following. You have a main that initializes the model, invoking once the initialize function. Then, until we are not at stop time, we step the model. We invoke the model step function that, starting from current state and current input, produces the output and the next state. Then we have to wait for the simulation step, so we wait for delta, and we repeat. So as you can see, the pseudocode that I placed here is reminding what we have seen about the way in which solver works, the Simulink solver works. We have an infinite loop. In each iteration of the loop, we evaluate the model, we update the state, we update delta, and we repeat. And this is what is happening. We have a loop that goes ahead until we are not at the stop time of the simulation. And in each iteration, we update the model. So we step the model. And then we wait for the delta time that we selected, and we repeat. When we are done, we can invoke the terminate function. So after that, we are done. So there is no need of using the memory occupied by the step function. Okay? Is this clear? So the model is translated into 3 files. This is because we selected the compact option. Among these 3 files, what is important is model.c, because it contains the code corresponding to the model. The code is distributed over 3 functions: initialize, step, and terminate. Then the other important file is rtwtypes.h, that contains the mapping between the Simulink native data types and the hardware-specific data types. If we go back to MATLAB, we can take a look to the files that are generated, and so we are more specific for this example. This is ERT-main.c. If you open it, you will see that well, we have the inclusion of the standard libraries plus controller.h and rtwtypes.h. We have controller.h because our subsystem in this example was called the controller, and so controller.h is where we have the definition of the data types for the model. Then if we go down into the main, we have that we call controller underscore initialized. So we are, sorry. Okay. Sorry. Okay, let's open ERT_main.c. As you can see here, we have the include files for the controller and the RTW types. So we have controller.h because our subsystem in Simulink was called controller, so the same name is used in the code generation process. Then if we go down and we look into the main, we can see that we have the invocation to the controller underscore initialize, so we are initializing the model. Then here we have a comment that is saying, attach RT one step to a timer or interrupt service routine with period of 10 milliseconds. This RT one step function is the function that invokes the controller step, and it must be executed once every 10 milliseconds. Why 10? Because this is the step size that we selected. 10 milliseconds is the time resolution of our model. 10 milliseconds is the parameter that we placed in the configuration of the solver. If you invoke this function every 10 milliseconds, you will see the same behavior on the target running this code that you have in simulation. Then, when you are done, you can terminate the model. So let's have a look at the content of this RT1 step. This is defined here. Besides some stuff here that is not relevant, you can see that we have the the call to the controller step. This is the function that allows the model to be updated. This is the function that executes one simulation step. Okay? Then we can enter into controller.c. This is the file that contains the model, and you can see that we have controller step, controller initialized, and controller terminate. The controller step is the function that implements the behavior of the subsystem. So what we are expecting here? We have a buffer. So we are expecting that the input is taken, multiplied by 10, and assigned to an output. And indeed, this is what is happening. Controller Y output B is 10 times controller U input A. If we look into the model, let me see if I'm able to do this. Look what we have here. The subsystem contains input A, again set to 10, and an output that is output B. So let's see what we have in the step function. Controller Y, output B. So Y is the symbol that the embedded coder associates with the outputs. So controller Y is the set of outputs for the controller. Then output B is the specific object inside the output of the controller. So controller Y output B is equal to 10 multiplied by controller U. U is the symbol associated with the input, input A, and it is exactly what we can see here. Input A multiplied by 10 associated to the output. Then, where does this value comes from? Well, we have among the arguments of the controller step, the RT controller T, controller M, this is the state, real T, controller U input A, so this is the input of the model, real T, controller Y output B, this is the output. Okay? Then you can see that this is passed by reference as a pointer because the function shall be able to update the value of that argument. For the model, is the same. This is passed by as a pointer because the model can be responsible for updating the state of the model, while the input is provided by value because that is something that we are not supposed to change, we just use it. Okay? Then, what can we see here is that this model is linked to the code. So, for example, let's imagine that we want to see on the Simulink schematic, which is the line of code corresponding to this gain. We can select the block, then we go to C++ code, and we can ask the tool to navigate to the code. So this will update the report in this fashion. So we have the lines corresponding to the Simulink block that are highlighted. Well, this is very convenient when you have a very complex diagram. You have a very complex Simulink block. Maybe you have some behavior that is not exactly what you are expecting, and so you want to understand how that block has been translated into code. So you can navigate the two in this way. And I think we can also do the same if we go here. I think it is possible. Where is it? Okay. So for some of the blocks, not for the input and output, it is possible to do the opposite. So you have the comment on the code that can point you backwards to the model. Okay? So do you have questions, doubts? Okay. So what we have seen today? Today we have seen how to configure a project so that it is a Simulink model that can be translated into code. We have seen some element of the code generation process. So I hope that you have now a clearer understanding of the link between model and C code. So we have most of the ingredients to move forward. So I propose to stop the lecture now. It is 9:45, so it is okay if we stop now. And then we meet again on Friday, going ahead with the controller modeling part. So please bring again the laptop on Friday, because Friday I want to start using Stayflow. So we have to do some practice together, okay? Do you have any question? Is there anything that I have to repeat? Okay, as final remark, please, now that all the vouchers are online, go ahead and start procuring the board so that we can then start using the board as well.